Okay, so my name is Ben Lev, and I'd like to tell you about one of the three experiments that we've been doing in my group at Stanford. These are my students who have been running the experiments, Yudan Guo, Ronan Croze, and then Brendan Marsh is a new theory student that we have. And I have this, none of this would have worked without Jonathan Keeling's advice and collaboration, and Sringo Balakrishnan, who's just up the road at the graduate college in CUNY. We also are starting to work with Surya Ganguly at Stanford, who's a neuroscientist. Okay, so the goal of this work is to introduce a new system for studying quantum many-body physics. And the new system that we're introducing is called multimode cavity QED, and I'll explain what I mean by multimode. And this specific subject of this talk will be how we can engineer interactions that will give us the many-body physics using photons mediated by the cavity between atoms and atomic spins. Okay, so the star of the show is this device here. It's a cartoon of a Fabry-Perot cavity, two mirrors, highly reflective with a group of atoms in the middle of it. Those atoms can be Bose-condensed, they can have spin, and we can image them directly using resonant light. Or we can pump them, with some transverse field like so. That transverse field can be near resonant with the modes in the cavity. Here I only draw two, but we can make cavities that have thousands of modes. And light can be transferred to the cavity, and that light can come out of the cavity and we can image it. So that's the scenario. So experimentally, kind of the achievement that we've been able to make is to create a high-finesse optical cavity so we can get in strongly coupled limits. Where one of the mirrors can move. We can move the upper mirror by millimeter up and down so that we can make very specific geometries that give us degeneracy points of the resonator that have thousands of modes that are degenerate. Meanwhile, we can do this while putting a Bose-Einstein condensate of atoms, rubidium atoms, between the mirrors, and we can do this every 10 seconds or so. So now let's go into what we want to do with this. All right, so the first slide here is to just explain what the theoretical scenario is. So you're familiar with cavity QED. You can drive the photon fields directly and exchange excitations at a rate g with the atom, say a two-level atom. That is position dependent, so if it's at a node or an antinode, you can go from 0 to maximum coupling. On resonance, this is what the interaction Hamiltonian looks like. But that leaves you liable to a lot of spontaneous emission heating. So what you typically do is tune the system off resonance, which in perturbation theory gives you something squared in the coupling constant. So that removes any sort of sign dependence of the coupling going from a positive antinode to a negative antinode. So that's a little unsatisfying. So we can fix that by pumping the atom directly. So it's kind of a symmetric case where you transfer excitations in the system first by going into the atom and then into the cavity. And then the interaction Hamiltonian looks like this, where you have an odd order of your coupling constant. So that's fun. So now let's see how we can build that into a basic building block of two particle interactions. So now let's say we have two atoms in the cavity, each coupling at a different position, x1, x2. And now each one undergoing interactions with the cavity with this kind of interaction Hamiltonian. But you can borrow that excitation that each atom puts in for an amount of time given by the detuning of the cavity, of the pump from the cavity. So amount of time proportional to 1 over this detuning, you can borrow that virtual excitation and exchange it between these two particles. Okay? So then what you get is this interaction squared divided by the energy scale that you've borrowed that excitation from. So this is the two-particle interaction Hamiltonian that we're going to exploit. And what's really neat about this is that you have the product of these two interactions and first order each of them. Of course, this only works if the detuning is much larger than the leakage rate of the light out of the cavity, which is easy to do. So going back to the story, so what you want to, what you can have fun doing is to exploit the shape of this interaction. So this coupling constant is really dependent on the mode shape of the particles of the photons in this cavity. And though usually in this field we only couple to the 0, 0 mode, we can actually couple to a lot of these different modes, or maybe them all simultaneously. And then you get an interaction Hamiltonian when you pull out the strengths of all of these. You get this kind of atomic constants over here, the maximum coupling strength and the pump intensity, times a product of these two mode functions. And that you can play with and have a lot of fun. Okay, so what can you do? So let's start very basic. Let's just say that the product of those mode functions is trivial, it's just two Gaussians, it's a 0-0 mode. What's the first thing that can happen in terms of organization physics? Well, as explored by many authors over the last 15 years, you can get self-organization. So let's imagine that you sprinkle into the cavity arrangement of atoms. They're randomly distributed, but basically if they happen to be at a node, let's say they don't exist, so you can get kind of like equal populations in the odd antinodes versus the even antinodes. Now, if you drive the system, say, a little bit below the resonance, ready tuned, you'll actually see, classically speaking, a phased array that is destructively interfering along this direction. You'll get subradiance if you have exactly equal populations. So you won't get any emission out of the cavity. But of course, there's going to be some statistical fluctuations of the populations in the even versus the odd states. And so depending on which sign this happens to have, you can actually get a potential that, if you look at the interference of this field versus the cavity field, is modulated between the even and the odd nodes. And if you use this red detuned light, this is an attractive potential. It's red detuned. So you form an optical lattice that has this emergent lambda structure, which then can be a runaway process if this fluctuation is strong enough, where all the atoms, say, organize into the odd states. Just take an example. And now you have a phased array that is super radiant in the sense that every emitter has a partner lambda away, and so they all emit in phase. And then you get enhanced emission coming out of the cavity. This is super radiant emission. It scales as the particle number squared. So that has been seen. This is one set of data where it's been seen. And you see a burst of light coming out of the cavity, all right? And this generally works if your collective cooperativity is greater than 1. You don't need the single cooperativity to be greater than 1. It's a collective effect. So you might ask what's happening to the atoms. So in position space in 2 dimensions, if you blow this out, they would look like a checkerboard. Of course, the Fourier transform of a checkerboard is some Bragg spots like so, which corresponds to the momentum. And you can observe that by letting the gas fall. As it expands, it's like going through a lens, and you can actually map position to momentum and image that. And this is what Tilman Esslinger's group did about 10 years ago. And you can see that the Bragg peaks of this Bose-Einstein condensate are exactly where you'd expect for this type of lattice. Now, what this really realizes is a non-equilibrium superradiant Dickey transition, or Heppley-Dickey transition. So, we've had a lot of discussions about that. You can do that in these sorts of cases because they're driven dissipative. They're in a rotating frame, and the no-go theorems don't apply. So you can also play games. So what is the order of this type of transition? What does this go into? It goes into a polariton condensate, tying to the theme of this meeting. But it's not an exciton. It's not the kind of electronic excitation. It's a dispersive coupling. It's a density wave. So you're condensing into a particular density wave. And that one here is deterministically defined by the boundary conditions of the mirror, so just be this checkerboard, okay? So that's the one that you condense into. Now you can play games with coupling to a few different modes, a few of those TEM modes, and then you can couple to other density waves, and this is called the turtle density wave that we discovered in our cavity. So that's called a supermode. Basically, the atoms are mixing a bunch of the modes together through their dispersive interaction, and then you condense into that density wave pattern. But that's basically what arises from this type of phase transition. So what about spins? So what if you replace the density excitations with spin excitations? What happens there? So the way to couple to that would be, instead of pumping with one frequency, you can pump with 2 colors of light that are tuned such that you realize this double lambda transition, double Raman transition, where the cavity photons form each one part of the leg of this Raman transition, and then the pump fields form the other legs between these hyperfine ground states of rubidium. And this is known to realize the Dickey model, which you are familiar with and has been posted many times during this talk here, during this conference, so I won't go into details. But just to note that this system does become super radiant when you reach threshold, and you can reach threshold in this kind of system because it's in a kind of a rotating frame. It's not really about ground states. So when that happens, what the picture you should have in your mind of spinful atoms that can move around is that below threshold you have this kind of low intensity square lattice that's just kind of emerging as you crank up your pump fields, and you have a Poisson distribution of particles, and they're all in the down state. Let's say they all start in the down state. But then when you reach threshold, you condense into a spinor condensate, spinor polariton condensate, where you break a Z2 symmetry of the kind of a superposition, a transverse superposition of up and down, either being right on the black checkerboards or right on the white checkerboards. Okay, so that gives you this kind of Bragg structure that you would expect, but with tied to spins. And you can see this experimentally. So if you let the gas fall, but then image the gas in a spin-dependent fashion, which we know how to do, you can see that the Bragg peaks are colored now. And if you ask what is the Fourier transform of this, it's exactly that picture I just showed you of this spin-decorated checkerboard pattern. So this shows that we can actually access spin degrees of freedom in this self-organized state. In the dispersive limit, again, when delta C is much greater than kappa and any other detunings, then this Hamiltonian can be rewritten as a quantumizing model. And that's really fun because now we can play games with exotic magnetism. Okay, so before I move on to those games, let me just explore one other cute thing that we've done, which is to create dynamical spin-orbit coupling. Now, the cavity field is a quantum mechanical field. It's A plus A dagger that has quantum fluctuations. If you can exploit the fact that it's dynamical to engineer something interesting, then you've now done some dynamical version of that. So say you have, again, your cavity, and these pump fields are now running wave pumps. So you have the same sort of coupling diagrams, but these legs here now can impart momentum. They're not standing waves, they can impart momentum onto your gas. Then what you can realize is the fact that below threshold in momentum space, you have a gas that looks like this. Instead of above threshold, you're having these 4 Bragg peaks, which was what I showed you experimentally before, where the sum of this has 0 net momentum. You can actually just do it in a one-sided fashion where you're imparting momentum through the coupling. And this looks like spin-orbit coupling because spin-ups are moving to the left and spin-downs, well, they're not moving, but in a boosted frame of KR over 2, this looks like spin-down is moving to the right and spin-up is moving to the left. That's what we mean by spin-orbit coupling. And it only happens at this threshold, and that's what we mean by dynamical here. So this is experimental evidence for that. So below threshold, that's this picture. And above threshold, you don't see those peaks anymore. You see these. And this resultant state of this is kind of a spin helix state that is kind of spinning along the x direction like so between these two. And that's something that is kind of a cute thing to do. But more importantly, this sort of basic nascent scheme could be used for creating dynamical gauge fields in the future, where instead of making spin-orbit coupling, you actually couple to an abelian or non-abelian type of gauge fields to do fun physics, and we have some ideas for that with Jonathan, and I can tell you about that later. Okay, but now let's go back to the main story, which is how do we do more exotic many-body physics than what I've showed you before. So we're just using a single-mode cavity before. In a single-mode cavity, all atoms scatter into the same global photon wave packet. So what does that look like? So here's a sketch of a cavity. Here's the TM00 waste of it. So if I pump it with photons, and here's like a little BC, not a big one, just a little BC, I scatter photons off of it, they go into the cavity, and they form this Gaussian profile of the mode shape of that photon wave packet. Now that photon wave packet can leak out of the cavity, and we can image it onto a CCD camera, and I just get this Gaussian profile, okay? Now, what's kind of disappointing is that if I pick up this BC with, say, an optical tweezers, so my green laser, I pick it up, and I move it around, no matter where I move it, either in this plane or somewhere else, everything that comes out will always look like a Gaussian. Basically, the only photon wave packet I could have in this cavity is that single mode, okay? The photon part of the polariton is boring. Like, there's nothing else going on there. So I like to fix that. And the reason I like to fix that is because if I only have that one mode, then when I exchange those photons between the atoms, it's the same everywhere in the cavity modulo the cosine wave of the standing wave of the cavity. And that results in a connected graph of all-to-all interactions. And that we know is liable to mean field physics. There's just really nothing I can do beyond that. All right? So what I need to do is figure out how to make local interactions mediated by photons. So I break some of these linkages. And what I'm going to claim and what we're going to show is that you need multi-mode cavities to do that. So how does that work? So multi-mode cavities provide frequency degenerate modes. So these modes that I showed you earlier, they have different spatial patterns, but if you play your cards right, you can actually have them resonate at exactly the same frequency. So if you make a certain cavity geometry where the tuning parameter of the cavity, the length of the cavity, is away from some interesting point, then you can resolve a bunch of modes. That's basically a single mode cavity. But if you hit this geometric condition set by Maxwell's equations, then you can compress all of these into a very small bandwidth and have more than 1,000 modes. And then how single mode it look or how multi-mode it looks like depends on how far you detune your pump from it. So if you detune it very, very far, this thing looks kind of like a delta function. If you detune it very, very close, you can start to resolve the difference. So you have two tuning parameters. One, the spacing between your mirrors, and also how far you detune. So those are kind of nice knobs that we can use to increase or decrease the degeneracy. So now let's describe how you make a local photon wave packet in a multi-mode cavity. So here's our cavity cartoon again. Let's tweezer a little BC in the middle, just a little clump of atoms. We scatter photons into the cavity, but now when we scatter them into the cavity, we're scattering them into a superposition of all the available modes at that position. All right? And so that's a summation over all of these Hermite Gaussian polynomials, and that gives you something that looks very, very spiked. In fact, if you have an infinite number of those, it looks like a delta function. Right? You don't have an infinite, it has some width. What does that width look like? Well, you can image it you can image this little packet, wave packet, onto a CCD camera, measure its radius, or you can calculate that with your friends like Jonathan. And what you find is some expression that looks like this, okay? Where the width of this is set by the number of modes. And so if you go to a single mode, it's as big as the TM00 mode. If you sum a lot of them together, they can get to be nearest neighbor, like, you know, with respect to the gas, like a micron, or even submicron. So, so another interesting fact about this is that the supermode that forms here, it's a spike of electric field. And that means that the single atom cooperativity is enhanced by that spike of electric field. So in our cavity, the single atom cooperativity is about 2. But now because of this spike and all the number of modes, it becomes 100 times larger. So in effect, the actual cooperativity of our system is more than 200. Now, I'm not sure about solid state systems, but in optical cavity QED, that's a record. And that's really fun because it's the cooperativity that allows you to judge how your quantum states that you're producing, the fidelity of the quantum states that you're producing. It tells you how much entanglement you have in the system. Basically, it comes in everywhere. So anything much greater than 1 is good, and this is certainly greater than 1. Okay, so can we observe this? So if we do this experiment with a single mode cavity, which we can do, so we just take our experiment and we just separate the mirrors so that you only have one mode present. That's just a turn of a knob in the laboratory. Then you always get this Gaussian mode no matter what. So this is the image that you get on your CCD camera. It's always a big fat Gaussian with 2 times the waist. There's nothing that changes no matter how we pick up the atoms and move them around. However, with the multi-mode cavity, if you do the same thing, then you get a tight little spot there. And what's really interesting is that this spot size, you can calculate, do the optics. It's limited not by the superposition, the available superposition of the modes, but it's simply limited by the size of the BC that we're able to tweezer in the middle. This radius here is exactly the Thomas Fermi radius of that Bose-Einstein condensate. So this is much smaller than this, so we know that we're making the super radiant supermode. And so in effect, what we have here is what I like to call an active quantum gas microscope. You may have heard these wonderful devices, first start by Marcus Greiner at Harvard, where you can image a quantum gas because you have a high NA lens. Here, we have a high NA lens as well. It's just you have another one, all right? So that means that not only do you get information out, but that information back reacts onto the system to actually motivate the interactions. So it's an active quantum gas microscope. All right, so now let's play some games. Let's put two two atoms or two packets of atoms inside the cavity. Now, the cavities that we actually use, I didn't tell you, but the multimode configuration we like to use is called a confocal cavity, where the radius of curvature equals the length. And in those, the kind of periaxial trajectories of light looks like these hourglass patterns. Okay, so this is the light propagating scattered from this atom. This is from this atom, like so. So this is the local wave packet that you would have for each of these atoms would be like so. All right, and of course that's what you would image coming out. But what's kind of neat is that you actually get a mirror image as well. Right? You get a mirror or a virtual image. Okay, it's like you put a mirror there and you have a virtual image. So you actually get 4 spots coming out. But this wave packet from this atom actually is over here. The atoms aren't, but the photons are over there. So if you pick up this atom, pick up that atom, and slide them back and forth, then you can actually overlap these photons with those photons and mediate interactions. Okay? So here's a movie of us doing that. So over here, only one of these is actually the real image. The other one is the mirror image from the other BC. Okay? So that's a neat trick that we're going to exploit in order to actually measure the photon-mediated interactions without having to worry about atom-atom collisions. So if we actually put 2 red dots here, the atoms would physically collide and that would obscure the result. But here, we actually can just exchange the photons directly and there's no actual hardcore collisions. So this is the experiment we're going to do and just focus on this part of the images. So we're going to measure the interaction energy as a function of the separation between a virtual image of other atoms and the real image of the original atoms. What we're going to do is we're going to increase the pump power and measure at what pump power do I start to see a burst of light coming out of the cavity. That's my threshold. And it turns out, that the more interaction energy you have, the less pump power you have to put in there. Okay, so the power at threshold decreases when the photon wave packets overlap due to the interaction. And so if I just plot the power, or actually the inverse of the power, then I can measure what the interaction energy is as a function of separation. So that's what I do here, or we do here. And so this is that separation normalized to the waist of the TM00 mode. This is all the interactions coming in. So there's a self interaction and a local interaction. And these different curves come about with different kind of spacings between the cavities, making more degenerate or less degenerate. And we just fix the detuning like so. Okay, we're not, in this plot here, I'm not changing the detuning. All right, so this is many modes coupled together. Of course, there's some aberrations, so they're not all resonant in the same position. And this, they're very much a single mode. So this broad plateau here is the self energy. That's just the photon wave packet coming to itself, and so it doesn't matter where the separations are, that's just the broad plateau. And then this little spike is that local interaction. And if you look at this, if you fit this functional form here and pull out what Cassie is, you can see that you can tune Cassie from anywhere from a micron in, we're resolution limited from the size of the BC, it's likely it's much smaller than a BC, all the way up to the waist, the TM00 waist of the cavity, about 35 microns. That's an order of magnitude tunability of the range of interactions. That's a lot of fun, okay? And we'll show you where we can exploit that later on. All right, so does this work for spin-spin interactions? So let's do the same. Let's go back to that story I was telling you where instead of just driving with one color field, we have 2 colors, and we can realize the spinful interactions. So what's the geometrical picture for spin interactions in the multimode cavity? You have, you pump the system, and photons will be scattered, say, by these atoms here, and then they can bounce off, and then they can interact with these atoms over there. That can just give you that local interaction if they're close enough. But there's also another type of interaction that can happen, and let me motivate how we can see that. So the light that comes off of this atom can resonate in the cavity, but it also can be imaged onto a CCD camera, and of course it has a local wave packet around it. Let's say that the light that we send in has, the phase of the light is 0, let's just set that to 0, and let's just say that the state of this atom is down. Then the light that comes out of here will just declare that 0 phase, it means it's down. So we can actually read off, if we can actually read the phase of this light coming out, we can read off the state of this atom, all right? And now let's say that there's an interaction between these atoms that not just local, but also mediate some sign-changing interaction, okay? Some possibly sign-changing. And let's, for fun, just call it antiferromagnetic. So that interaction would cause these atoms to be, say, spin up, and then because we've declared that this is the right mapping, then pi light actually means that it's spin up here, okay? So just by measuring the phase of the light coming out of the cavity, we can actually imaging the light that comes out at the atoms, we can actually detect whether we have down atoms or up atoms. So we don't actually have to go in and measure the spin state of the atoms anymore, which is really hard to do. That's what traditional quantum gas microscopes do. We can use our active quantum gas microscope to do that and also give our interaction. So direct spin readout is possible via the phase of the local light emission. And then, of course, there's a lot of light circulating back and forth, which is reinforcing this coupling to make it very, very strong. In fact, it could be on the scale of megahertz, whereas the scale of the spontaneous emission, the heating rate, which is like the horrible thing that you don't want to have happen in your system, can be tens of hertz. Okay, so you can have large separation of time scales, yet interesting interactions. So now I want to motivate how you get an antiferromagnetic interaction. I told you how you get a local interaction, you just overlap these spots. But how do you get this signful interaction? So where do they come from? They come from GUI phases. So one way to do it is through GUI phases. So what are GUI phases? So even with water waves, and presumably gravitational waves, any wave, sound waves, if you focus them, they will undergo a phase shift. The phase of the light will actually undergo a phase shift. And there's many explanations for this. I will not go through them right now, but we can talk about them later. But basically, the phase shift that you get through a focus increases as the order of the mode. So the more kind of transverse wiggles you have, the larger the phase shift, okay? You can kind of get into it why that might be. And so when I took this sum before, I was ignoring something. Okay, I was just looking at space, but each one of these modes has a phase. All right, and so when I take the sum, I actually have to sum over all these phases, but each of these modes has a different phase, and so that's going to lead to something complicated. All right, and so when I take the sum like so to get the interaction, it turns out that in addition to that self-interaction and the local interaction, I end up having a non-local interaction as well. And funny enough, it looks really weird. It looks sign changing. It looks like cosine R1.R2, all right? That I've never seen in nature in any other context, and that comes from wave physics, all right? So that's a pretty neat thing. It's neat because, of course, it changes sign, and it's very nonlinear. Let me give you one other piece of intuition about where this is coming from. So I was drawing the paraxial picture of the ray tracing dynamics of the light going in the cavity, but really what's going on in the center here is not like two little beams crossing, it's actually, this is more of the Gaussian picture. You actually have a very bizarre interference pattern. This is the non-local part of this wave packet, is this interference pattern here. You have a local wave packet around here that's kind of whizzing about, but then this is the non-local part. And you can think about these fringes as coming from just simple Fourier optics. If I take a spot that's off-center, so we focus on this spot here, and I ask what is its Fourier transform, it's a grating. All right? So what's happening here is because I'm confocal, all right, which is what gave me the multimode distribution and multimode degeneracy in the first place, I have a particular boundary condition on the focal length and the path length of the light. So as I go from here to here, I'm actually taking a Fourier transform. So this light here is just the Fourier transform of this local photon wave packet. But of course, if I put an atom there, it interacts with that non-local part, not just the local part, and vice versa. And if you look at what happens when you're interacting the non-local part of two spots coming together, you work it out, that's what you get, okay? In some hand-wavy sense. So that's a really neat thing. So how can we observe that? So again, we do our experiment. And now what we want to do is actually look at the spins of the atoms to see whether that cosine interaction is making them flip sign up and down by imaging the phase of the light coming out of the cavity. So how do you do that? You take another laser beam that's exactly the same frequency and phase lock to the cavity light and beat it against it outside the cavity on a CCD camera. That's what's called spatial heterodyne or holography, actually. You get these stripes and you look at the wiggliness of the stripes and that tells you the phase. So if you do this in a real experiment, now this is real data here, okay? and you have two atoms in there, or two clumps of atoms, then you can see that depending on where the spacings are, if you're in one particular spacing, then that cosine term gives you a ferromagnetic interaction. You get the same phase, okay? But if I move one almost imperceptibly from the other, it's hard to tell that they're moved, but if I move it so that the cosine now flips sine, now I have a blob of atoms that has the opposite phase, meaning that it's spin down. So these are spin up, this is spin up and spin down, and I've realized antiferromagnetic interaction. So, okay, so what's really going on here is that this is a spinor polariton condensate. So this is both spin and checkerboards here locked and here like so. So this is a little clump of atoms like this. This is a little clump of atoms with the opposite sign. But never mind. If I were to put a 3D optical lattice to restrict the motion of the atoms, I would just only have that spin state, and it would really just be pure spin. But it doesn't really matter. These are pseudo-spins up and down. Okay. All right. So this is demonstrating the sign-changing nature of the interaction just by moving them back and forth, and it realizes this Ising interaction Hamiltonian where this Jij matrix can now flip sign, and that's really, really great because now instead of having two atoms, what if I had a third? And I arrange them in such a way that I have a negative product of the interactions. Then I have geometrical frustration, and that's fun because now I can have glassiness. Okay? And glassiness is a really exciting thing to study. Okay, so what we've done is to provide all of the ingredients needed to make a quantum optical spin glass. So we can put the atoms anywhere we want with optical tweezers, and now we know how to make hundreds and in principle thousands of arrays of tweezers using technology developed by other groups for Rydberg atoms. We can do spin interactions, so we've demonstrated spin. We can do tunable range interactions, which will be fun to create kind of graphs that have arbitrary connectivity, not just all-to-all. We have signed interactions, so now we can make geometrical frustration, so we can make non-trivial graphs that can represent NP-hard problems. And we can read off what's going on. We can actually detect what the spin states are, even in real time in principle, but without having to go in and look at all the atoms, we can do that with holography. So we have all the ingredients. So where are we going with this? So what we like to do is to explore kind of a 35-year-old problem, the spin glass problem, which is a very difficult problem to solve in statistical mechanics. And what's known about it is that in infinite dimensions, or all connectivity, has a very bizarre solution called replica symmetry breaking solution, which has a lot of application in computer science. But nevertheless, we don't understand when you start breaking some of the linkages and go to finite range, whether that scenario persists or whether you get some other bizarre type of scenarios. No one's really been able to address that. And we can actually experimentally make the same Jij matrix each time, make replicas, and compare them in system sizes that are not possible otherwise numerically. So that's what we're excited to do. Of course, this has implications for computation, which I'll explore now, and this is my last slide. So what are the future directions with multimode cavity QED? So going back to the beginning, I said that when you scatter light into the cavity, you make this lattice. In a multimode cavity, that lattice is fully emergent optical potential. It's not just the amplitude, but it's also the positions of the minima. This lattice actually has phonon excitations. It has real Goldstone modes and phonon excitations. If you do this in 2 dimensions, we've calculated a long time ago that you should be able to find a quantum version of an unusual type of phase transition called a Brzozowski transition, which results in a quantum liquid crystal state, or a smectic, or various smectic-like states that would then be superfluid. And this is because you can engineer a circle of soft modes that you can condense into. This sort of physics is also explored in high-temperature superconductors, and you can ask the relations of these kinds of physics to other things. Second, I told you about making dynamical spin-orbit coupling, but using a slightly different scheme, we can demonstrate things like Meissner effects, or more broadly, dynamical gauge fields, which is fun for many reasons. This is an example from the paper we wrote with Jonathan Keeling, where you can see that you can expel vortices from an atoms coupled to a cavity, just like the Meissner effect, but now using the photon-mediated interactions that are dynamical. And then I mentioned that we would like to make a spin glass to look at what is the intrinsic order of spin glass physics. and even quantum spin glass physics, where there's some entanglement among the atoms. But then, of course, this also enables neuromorphic computation, where this JIJ matrix can embed hard optimization problems, and we can then exploit the driven dissipative nature of the cavity system to help us organize into the optimal state in a way that it may be better than traditional annealing, quantum annealing, and those techniques. So that's a very exciting direction. So with respect to this meeting, we're also working and just talking with Victor Galitsky and as well as Jonathan on how to explore cavity-induced unconventional superfluidity by exchanging the rubidium atoms for fermionic atoms. In my laboratory, we also do experiments with dysprosium, which is a fermion, or can be a fermion. And then using the cavity to induce pairing, okay? And a general goal then would be to use the system as a test bed for studying how driven dissipative correlated matter can arise in such a system. Can you encourage the formation of an unconventional superfluid with the cavity? I mean, I know a lot of you are thinking about that, but we can actually test that with the fermionic atoms in a way that gives us a lot of accessibility and control of dimension, disorder, and so forth. And then we can simultaneously create charge density waves and the superfluidity and see what kind of competition there is, just like there is in high TCs, and how that can act to suppress or enhance those modes. And then apply these lessons to the solid state after we've learned this. Okay, so with that, I would like to return to a picture of all the people who do the real work. These are the folks on multimode cavity QED, and of course Jonathan is here, and I encourage you to talk to him about our work. And just a blatant advertisement for other things we do. We look at quantum integrability breaking in 1D gases using a dipolar Newton's cradle. So we've created the first system that looks at a near integrability and thermalization in these systems. And then we've invented a new type of microscope using a Bose-Einstein condensate that we put near any material we like, and we can cool that material and run current through it and image it with like a scanning probe microscope. And we've successfully done that now with electron pneumatics and nictides. So I'd love to tell you about that as well. Thank you for your time.
Thank you. I'm sure there are lots of questions.
You could just be hungry, it's all right.
Peter?
Yeah, sorry, I'm confused about something. Well, actually, I'm confused about many things, but let me just tell you about one thing I'm confused. In the lattices you're constructing, typically you have interactions which are effectively long range because they depend on the mode product, and therefore they depend on R1 and R2 separately and not on R1 minus R2. The way you get finite range is by cutting down the number of modes. Doesn't that also then mean that intrinsically you're reducing the size of the system that you can simulate? What's the trade-off between the range and the size?
You've been led astray somehow. So it is true that the product is of two functions that are just R1 and R2. Right. But the superposition of that can actually give you an interference pattern that allows it to be either translation invariant or not. You can choose one way or the other depending on how you look at the photon wave packet, whether the local part or the non-local part. But so it has no finite size limitations other than the mirror diameters.
Okay, I guess I don't understand. Never mind, I'll figure it out. Okay.
Yeah, when you take that sum, you can get something that looks like exponential minus delta R. So you can actually get something that is the difference between the two. Or not, depends on which modes you take.
But I mean, it must surely depend on how I register those. Again, there's sort of a natural sort of microscopic periodicity in there. Mm-hmm. And therefore, on some scale, which is quite short, mm-hmm. There's a. So I mean, what you showed are things where I'm moving actually relatively short distances and changing interactions at long lengths, and I sort of understand that. Mm-hmm. But then if I bring it back into resonance,
So you're right in the limit that I have an infinite number of modes.
Right.
Then I get just delta function supermodes at each atom. Right. And of course, then there's no delta R because it's a delta function. So you are right, actually, that I am cutting off some of the modes, and that gives me some width.
Okay.
But that's
But you're saying that that isn't a particular trade-off in terms of the size of the system?
No, because I can form, I can do that at the center of the cavity, and I can do that a mile away from the center of the cavity, as long as my mirrors are a mile wide, right? Okay, they're only a millimeter wide. But yeah, I can do that either way. And so there's no finite size limitations, but it is a truncation, but it's a very, very practical kind of truncation.
So the dynamical gauge field you mentioned, so is this the right way to understand it, that if the atom moves, it will change the let's say, the occupancy of the multimode cavity, which will then act back?
Yes, it's a feedback process.
So what is the role of dissipation in this case? I mean, can you really have a parameter regime where dissipation can be neglected and you simulate a model with
So that's a very good question. I could envision it coming in two ways. One, the dissipation always comes in to change the universality classes of whatever transition you go into when you start populating the cavity. So it changes the critical dynamics of that. It also sets effective temperatures of the system to tell you whether you have more classical or more quantum critical dynamics. So I know those two things. You're asking more about a third thing, whether it can change the whole entire character of the dynamical. That, through retardation effects, maybe, but I don't know.
So perhaps a general question about the last part of your talk. So what are the constraints about the number, I mean, like the quantum spin glass emulator, okay? So what are the constraints on the number of spins and their connectivity that you envision?
Great. So there's different modes that you could run the system in. If you want to maximize the number of spins, you can go up to 10 to the 7.
Wow.
But then you would have a random GIJ. You couldn't just say, I want to have the same GIJ each time.
No, but imagine I do want a random GIJ.
If you want a random GIJ, I'd give you 10 to the 7. Okay. And I could have a fixed statistical distribution of GIJs. If I wanted to create the same GIJ each time, say I wanted to optimize a particular graph, like a max cut graph, then I'd be limited to about 10 to the 3, 10 to the 4 spins. That's still okay. Yeah.
So could we think of an interesting mode in which the quantum spin glass phase melts is actually into one of these /JFCA liquids, right, or SYK models? Is that something we realize?
I don't know. I don't know. I have to understand that a little bit better. Yeah, I'd like to learn more about it. Yeah.
More questions?
Can I really understand the J interaction as instantaneous, or are there retardation effects? What are the energy scales?
Right. So the virtual photon lives for a time scale of 1 over delta C. Delta C is like a megahertz to 10 megahertz. So it lives for like a microsecond. And yeah, I don't think there's many retardation effects because it's also reinforced by the cavity. Then the retardation effects would come from kappa, and kappa is 100 kilohertz, which is, yeah, orders of magnitude different. That's when you get the retardation.
Okay, well, let's thank Dan again and
Okay,
all the
thank you.
speakers.